The last few classes, we've been discussing the numerical solution, mostly of partial differential equations. Last class was also coupled differential equations. We were using the relaxation method in the case of the Laplace equation. We used leapfrog method in the case of diffusion equation and wave equation. The Laplace equation was time independent. The diffusion equation and the wave equation were time dependent. So that dictated our choices about relaxation method and leapfrog method. I'm going to move on to the last topic, last module for this class, which is the overarching theme of it is digital signal processing. We're going to start with some work on processing in terms of filtering. We'll move on to some processing in terms of interpolating. Overall, it's really a theme of learning from digital signals. Today's class will look at building a low pass or a high pass digital filter based on a low pass, high pass RC circuit. We'll turn that into a digital equivalent, a digital filter. The low pass filter that we'll build today it's used in machine learning. It's used in gradient descent and removing noise and gradient descent in machine learning. The high pass is used in also machine learning. It's used in edge detection and feature detection in machine learning. So both of the filters we talk about today, the low pass, high pass filter, they are both used in machine learning applications. I got one slide that introduces digital signal processing, some terminology, some reasons why we're interested in it, some facts about it. I got another slide specific to digital signal filtering, some terminology, again, why we're interested in it, some facts about it. So we'll go through those two slides. Then I'll get into specific cases of digital signal filtering, the low pass RC filter, the high pass RC filter, and then we'll go on to the computer code. So we think of a signal as a quantity that varies with some other independent variable. So it might be a quantity like voltage varying with time. That would be a classic variation of some dependent variable, the voltage, varying with some independent variable, the time. So that's going to be our signal, or that's going to be what we call our signal in digital signal processing, some dependent variable varying with some other independent variable. A sequence, a series of voltages varying in time, in a time sequence. That data typically would come from some sort of detectors, some sort of sensors. In that data, in that signal is some interesting information. There's also typically in that data some noise, and we often use filtering or processing to extract the signal from the noise. In the digital case, we might be digitizing data with a certain number of bits at a certain rate. So as an example, in a digital case, you might digitize voltages with using 12 bits. I think that allows you to go from 0 to 10 to 24. And you might digitize at a rate of 1 megahertz. So 1 million of those 12-bit samples per second. So that would be an example, very specific, very concrete about what rate we're digitizing at and how finely or coarsely we're digitizing. So that's going to be our data, our digital data. And then digital signal processing and digital signal filtering are algorithms that we apply to that data, or methods, techniques that we apply that data to select the information or the signal that we're interested in from the noise or the background that is present. And that digital signal processing includes filtering that we're going to discuss today. It includes cleaning of data. We're going to discuss that, I think, after Thanksgiving. It also includes transforming the data. We'll be discussing that too. And digital signal processing has become ubiquitous across science, engineering, medicine. So, one great example of it in physics is the digital signal processing that was done to extract the signal of gravitational waves from the data that was collected. That data has the gravitational waves embedded in it, but there's a lot of noise and background in that data. And complex digital signal processing was used to extract the evidence of gravitational waves. Another example is that digital signal processing is used a lot in medical applications. So things like MRIs or things like electrocardiograms. They produce streams of data, and digital signal processing is applied to those streams of data to extract and diagnose based on that data, to extract information, to learn about the patient from that. Okay, filtering. I want to say a few words about filtering. Filtering we often think of as we filter data to separate the signal that we're interested in from the noise that we're typically not interested in. So maybe restore the signal after it's been distorted by the environment, something like that. You can do filtering in the analog domain. You can do filtering in the digital domain. The filtering in the digital domain far outruns the filtering in the analog domain. In a digital domain, I'll just give you one example. You can build a filter, digitally build a filter, i.e. develop a digital algorithm for a filter that will pass all frequencies up to, say, kilohertz with a gain of 1. And then within a space of 1 hertz out of that 1 kilohertz, attenuate all higher frequencies by a factor of 1,000. So that would be an impossibility in analog domain. That is a possibility in the digital domain. So that's why filtering nowadays is often done digitally, whereas in the past we would have done it with analog signals. So it's very, very powerful technique. When we talk about filters, there's several ways that you can characterize them. We're gonna look at these different ways of characterizing them. You can characterize them by their frequency response. You can characterize them also by their impulse and their step responses. So these 3 ways, frequency, impulse, and step responses, are 3 different ways to characterize digital filters. Sometimes one or the other is useful. They're all equivalent to one another. So if you know the frequency response, you can figure out the step and the impulse response. Or if you know the step response, you can figure out the frequency and the impulse response. So they're all equivalent to one another. There's 2 basic categories of filters. One we call convolving filters, and one we call recursive filters. And these sort of describe how these filters work. Here is an example of a convolving filter. So in this example of a convolving filter, we imagine a input signal, digitized input signal, and we're representing that digitized input signal by these variables xn minus 1, xn minus 2 are a series of samples of the input. And then we're going to imagine the output by this variable y. So yn plus 1, yn plus 2 would be a series of outputs. And we can write for the convolving filter the output value of a particular sample, say the nth sample, in terms of the input values up to that nth sample by this little convolving filter equation here. So this says that the nth sample of the output of the convolving filter, yn, the output of the convolving filter, is some superposition or some sum of the input xn, so at the same instant time, the previous input, so that's xn minus 1, the previous input to that xn minus 2, and so on and so forth. So a convolving filter has its output at a particular tick or time defined by the inputs at that tick or time and the inputs at previous ticks in time. So it looks back in history at the past input. So that's what's being described here, and it carries with it, depending on how far you look back in time at the values of the input, it carries with it a number of coefficients, a number of constants, which are describing exactly how you combine the current input with the prior sample's input, with the prior sample to that's input, and so on and so forth. So these B0s, B1s, and B2s, and so on are coefficients that define your particular algorithm. They define your particular convolving filter. Recursive filters. So recursive filters don't just use the prior inputs to determine the output, but a convolving filter, a recursive filter will use both the prior inputs to determine the output and the prior outputs can be involved in the output value. So here, again, the x's are the inputs, the y's are the inputs, the labels on the x's and the y's, the n minus 1, the n minus 2s, those are indicating which particular sample on the input or the output. And in a recursive filter, not only does the output depend on the input values, the current one and the prior one, but it depends on the prior output value and the output values before that. So that's what I'm writing down here. So not only do we have the coefficients B1, B0, B2 that we're multiplying the input values, but we now have a new set of coefficients that I called A0 or A1 that are multiplying the prior output values. And because this filter, the recursive filter, involves the output, we call it a recursive filter. It's like a recursive relationship, rather than the convolving filter is just involving the inputs. So it's a convolving filter. If you want to think of them this way, in one case, you don't feed back the output. There's no output feedback in the convolving filter. In the recursive filter, you are feeding back the output. And so it's a filter with and without feedback. These two categories here. They differ in that a convolving filter has some memory of the input, depending on how many samples you walk back. But the recursive filter can have infinite memory of the input because it's feeding back the output into the next sample. So they also differ in a finite memory versus an infinite memory for the convolving and the reverse conversive filters. This is just a diagram. Maybe this helps in clarifying how they define how they might work. Top plot is the convolving filter, and the bottom plot is the recursive filter. And the diagrams basically have coming in on the left side, you've got the input signal. Out on the right side, you've got the output signal. So in on the left is the X values, and out on the right is the Y values for each of these indices N, these little ticks or time intervals N. And in the case of the convolving filter, we just make the output from some superposition of the input, the current and the past inputs. That's what's happening upstairs here in this diagram. In the recursive filter, then the output is made from some superposition of the input values, the current one and the past ones, but also it's feeding back. It's feeding back the output, and that's also past outputs are superimposed in the current output. And so that's how there's no feedback in the convolving case. There is feedback in the recursive case. There is a limited memory in the convolving case. There is an infinite memory in the recursive case. Okay, I got a few slides on RC filters, low pass RC filters and high pass RC filters that you've met before, just describing how an analog circuit RC filter would work as a high pass filter, a low pass filter. So we're going to just remind ourselves of low pass, high pass RC filters. Well, then, once we reminded ourselves, write down the differential equations describing low pass, high pass filters, turn those differential equations into difference equations for the low pass, high pass filters. And once we got the difference equations for the low pass, high pass RC filters, we'll see that we can write down they essentially are the recursion relations that define the digital version of those filters. So we're learning how to go from a current knowledge of analog RC filtering to an algorithm for a digital low pass, high pass filtering. That's the plan here. So this is a low pass RC filter. Inputs coming in on the left-hand side and outputs on the right-hand side. So they're just called V in and V out. And there's a pair of terminals on the left across which we apply the input, and a pair of terminals on the right-hand side, which we see the output of the filter. And the low-pass RC filter just has this arrangement here. It's a resistor and a capacitor in series, and the output is across the capacitor. So that's the arrangement. With that arrangement, if you put for example, if you put a voltage step on the input, you'll see a voltage step on the output, but there's a time scale that's introduced for the step, a time constant that's introduced for the step, and that's essentially the filtering going on here. So this is the step function description of the filter, where you put in a step function, you get out a filtered version of the step function. And in this case of the low pass filter, what you see is the time constant in the output side. You see the time constant of the filter. Look, when we apply this voltage to the filter, we're going to this step function to the filter, we're going to charge up the capacitor. So there's a period in which there's a current flowing as we charge up the capacitor, a period in which there's a voltage across the resistor, and there's only a fraction of the input voltage across the capacitor. So it's that period that is the growth of the voltage across the capacitor. But once we charge fully up the capacitor, or the charge is stored on the capacitor, then there's no current flowing in the circuit. And you simply see with no current flowing in the circuit, there's no voltage drop across the resistor. We see the full voltage across the capacitor. So that's an arrangement that gives us a low pass filter. Here's just the discharge of the capacitor, but same ideas, that you put in a step function and you get out a step function with a time constant that reflects the time constant of the filter. This is the use of the RC circuit as a high-pass filter. So it's the same arrangement of a series capacitor and resistor, but now the input is across the series arrangement again, but the output is across the resistor in this case. So in this case, if we put in a step function again on the left-hand side, we get out this impulse with a time constant on the right-hand side. So what's happening here, you put in the step function. When you apply a voltage across the resistor and capacitor arrangement, again, that voltage will cause a current to flow, which is going to charge up the capacitor. So while the capacitor is charging up, there is a current that's flowing, and we're seeing the voltage across the resistor due to that flowing current. But once the capacitor gets fully charged up, then the current flowing through the resistor onto the capacitor, that ceases, and we'll see no voltage across the resistor because there's no current flowing through the resistor. So this is the result of a step function to the high-pass filter. And again, when you apply a step function, what you'll see is the time constant, characteristic time constant of the filter. So the time that it takes this impulse of current to die off is the time constant of the RC circuit. So it's how we see the time constant of the RC circuit. The same would be true if we were to discharge the now charged capacitor, right? We have a step function from the voltage across the capacitor down to ground, then we would see a corresponding output that is an impulse. That is reflecting that current only flows through the resistor while we're discharging the capacitor for a brief amount of time. And the time constant of that current is determined by the time constant RC of the circuit. So that's a reminder of stuff I'm sure you know. A couple of pictures I wanted to show you. So this is for the low-pass filter. Now let's imagine we take that low-pass filter circuit, that very simple circuit, and we apply at the input a sinusoidal signal. So a signal that's just oscillating as a sine wave or a cosine wave. If we apply that at the input, then we're going to look at the output. What do we get out the output? With the low-pass filter, if the applied sinusoidal input has a low frequency, a frequency that's lower than the frequency that's determined by the time constant of the RC circuit. So the product of R and C is a time constant. The inverse of that is a frequency. If our applied frequency is lower than that, so the voltage is varying slowly, then that signal will pass through the filter. And we'll see that signal on the output. If that input signal is a high frequency, so it's rapidly changing, then that signal, when applied to the low-pass filter, will not pass through the filter. And we'll see no output on the output side of the filter. And so those are the two extreme cases. If you've got a low frequency, if it's much lower than the frequency corresponding to the time constant of the RC circuit, then you see the output is simply the input. If you've got a high frequency, meaning if you've got a frequency that's much higher than the time constant of the circuit, then the inverse of the time constant of the circuit, as determined by the RC values, then you get no output. In between those, then you get a attenuated output of the original signal. And this plot here, just focus on the one upstairs, vertical axis is the amplitude for the output. Horizontal axis is the frequency of the sinusoidal input. FC is this critical frequency corresponding to the inverse of the time constant. If you're lower than that frequency, the signal passes through. That's the one here. If you're much higher than that frequency, then the signal is completely attenuated. That's over on the far right here. And if you're in the region of that frequency, well, you get an attenuated signal passing through. And actually that attenuated signal has its phase change as it passes through. So this is why we call this a low pass frequency filter, because it passes low frequency signals, but it attenuates high frequency signals. And this is looking at that filter, not as a step function, but looking at it in time domain, looking at it in the frequency domain. Okay. This is the same thing for the high pass filter. High pass filter, we reordered the capacitor and resistor. The output is the voltage across the resistor rather than the voltage across the capacitor. Then, if we want to look at the frequency characterization of the high pass filter, then we can put in a sinusoidal signal on the input and look at the output. If the sinusoidal, with a high pass filter, if the sinusoidal signal is a high frequency, if it's varying rapidly with time, then it just passes through the filter unattenuated. If it's a low frequency, then it's extinguished by the filter. It doesn't pass through the filter. Where low and high frequency means low and high frequency, much lower or much higher frequency than the frequency that's determined by the time constant of the RC circuit. So RC is a time constant. The inverse of that is a frequency. I'm calling it the critical frequency here. If you're much higher than that frequency, you'll just pass your signal. You just pass through the filter. You're much lower than that frequency, then you're completely attenuated, extinguished by the filter. And if you're somewhere in the middle, in the region of the critical frequency or the region of the time constant, then you're partially attenuated. So again, if you focus on the top plot here, vertically is the gain of the filter. Horizontally is the frequency of the signal being applied to the filter. If you have a high frequency, much higher than this critical frequency, the inverse of the time constant, then you just pass through the filter with a gain of 1. If you have a signal with a low frequency, much lower than this critical frequency, then you're completely extinguished by the filter. And then in between the region of FC, or the corresponding time constant, you are partially attenuated, and also your phase is changed. So that's the frequency domain for low pass and high pass filters. Now I got 2 slides. I put 2 slides in here. One to write down the differential equation describing a low pass filter, and then turn it into a difference equation. And I'll walk through this slide for the low pass filter. I've also got it in the notes the corresponding case for the high pass filter, writing down the differential equation describing the high pass filter and then turning it into a difference equation. I'll just go through the low frequency case. I just wanted to document in here the high frequency case. In both cases, by writing down differential equations, calculating the difference equation, I'm able to extract the recursion relation that maps the input to the output so that we can develop an algorithm for a digital filter. So on the right-hand side of this slide is an equation that describes how to implement the digital filter for the low-pass filter. And on the second slide, the right-hand side is how to implement the algorithm for a digital filter for a high-pass filter. Here's a low-pass filter again. Remember, simply a series resistor and capacitor. The input is applied across the series input and capacitor. The output is the voltage across the capacitor. And a high-pass filter is just the reverse of that. Again, it's a resistor and a capacitor in series across which we put the input, but we're going to take the output in a high-pass filter, take it across the resistor rather. So that's the circuit. V in is, in my differential equation, the input voltage. And so this is, when I'm thinking of V in, I'm thinking of an analog voltage that's varying continuously with time. V out is the output voltage. Again, for the V out, I'm thinking of an analog voltage that varies continuously with time. Then I can construct differential equations with V in and V out because they're continuous variables, dependent variables that depend on the time, the independent variable. When we come to turning them into a difference equation and a recursion relation for the filter, I'm going to replace the V in, the continuous variable, with Xi, which is the discretized version of the input for the ticks labeled with I. And Yi, that's going to be the output, the discretized version of the output in the recursion relation for the filter with I, again, labeling the particular tick, so the particular interval that is measured. Okay, over here I'm building a differential equation over on the right, turning it into a difference equation. Where do we build the, or how do we build the differential equation? Just Kirchhoff's rules. Kirchhoff's voltage rules for the voltage that is applied across the circuit and how it gets distributed between the elements in the circuit, which is just the resistor and the current and the capacitor. And also essentially Kirchhoff's current rule that the current that's flowing through the circuit will be a current that flows through the capacitor and the resistor in this series circuit. So we're using both of those rules. So the input voltage applied across the pair of terminals on the left is related to the output voltage, what we get out across the terminals on the right, by this little equation from Kirchhoff's voltage law, is that that input voltage is shared between the two components in that circuit, the resistor and the capacitor. They're in series, so that the input voltage equals the voltage across the resistor plus the voltage across the capacitor, which is the output voltage. So this is Kirchhoff's voltage rule applied to those two elements. What we wrote down here, the voltage across the resistor, I wrote it using Ohm's law as current times resistance, because I'm going to substitute in my understanding, again, for current law of what this current is. This current that's flowing through that resistor, well, it's that current that's charging up the capacitor. So that current is the rate of change of the charge on the plate of the capacitor, which determines the rate of change of the voltage on the face of the capacitor, and the rate of change of the voltage on the face of the capacitor, the rate of change of the output. So this relates the current to the output voltage also, rate of change of the output voltage. So I can replace this current with this rate of change of the output voltage. It's this equation here. This is the differential equation describing the circuit. So it's a differential equation, ordinary differential equation, first order with respect to time. It incorporates the input voltage that we're going to specify, and then it tells us the output voltage in terms of the circuit arrangement, the circuit components, the resistor and the capacitor. Let's turn this into a difference equation now. So we've written down an analog differential equation based on current and voltage rules. Now we're going to turn it into a difference equation that we can use in an algorithm in our digital signal processing. So I'm just replacing the continuous variables, which are the input voltage and the output voltage, with their digital equivalents. The input is just going to be the xi's, so it's like an array of input voltage values in these little discrete intervals. V out is the yi's, it's just again an array of voltages in these discrete intervals. The xi's are what we're going to specify, or yi's are what we're going to calculate. So that's the left-hand side. On the right-hand side, we've got the parameters of the circuit, R and C, and then we've got the differential of the output voltage. We've just got to write that as a difference equation. Well, we've done this many times now. We've written differentials, first order differentials, recognizing them as slopes, as the discrete changes in the dependent variable. So that's the y value divided by the time interval of the independent variable. So this is just recognizing that this differential is the slope, and in using first order Taylor expansion, we can write that slope by this approximation. And so I plug that in. At that point, you've got an equation that contains yi in terms of the xi and the previous yi minus 1. So you can see that this is going to be, it's not going to be a convolving filter. If we're going to write it as an equation for yi, it's actually going to be a recursive filter, because if you rearrange that for yi, yi is going to be a function of xi, the current input sample, but also the prior output voltage, so yi minus 1. So this is just, this line here is just rearranging our difference equation in the form that we wanted to implement it in our code. Says that the output sample yi is determined by the input sample xi and the prior output sample yi minus 1. The quantity alpha is just a convenience, right? It's just the ratio. There's 2 times specified in this equation. One time is RC. That has units of time. That's a time constant. The other time that's specified in this difference equation is that delta t. That's the time between your successive samples. That's the tick of your clock. So in implementing a RC filter, low-pass filter, on your digital signals, you have 2 times inherently, one of them the time constant of your filter, and one of them the time interval of your data. And alpha is just a very convenient quantity that involves the comparison of these 2 times for writing down your recursion relation here. So look, there's going to be extremes of alpha. If the time constant is very small, that would be a high frequency. Uh, a small RC is a small time, which is a big frequency. If RC is very small, then alpha is roughly 1. So there's one kind of extreme of this equation. You just get this PC. You get very little feedback. If RC is big, let's imagine now RC is much bigger than the time interval between your samples. If this is big, then alpha becomes very small, and so feedback starts to dominate your recursive relationship here. So there's different extremes where the first term or the second term become more or less important, depending on the relative sizes of these two times that characterize your sampling rate and your RC time constant that you're filtering. Okay. So now we can go on and implement this. As I say, here's the high-pass filter case is the same task. By Kirchhoff's laws allow you to write down a differential equation. We can turn it into a difference equation with Taylor expansion. We can rewrite it as a recursion relation for the high-pass filter. And here is that recursion relation for the high-pass filter. One thing I'll say about these two recursion relations for the RC filters, the high pass and the low pass RC filters, is that they only involve the current sample and the prior sample of the input and the output. There's only a couple, 2 or 3 terms. So this makes these filters rather fast to implement. Other filters might involve many samples in the history of the input and the output. There are filters that are called rolling average filters, for example, that may average over many, many samples. So they will be time consuming to implement because you've got to perform a lot of calculations. Well, one thing about these simple RC filters is that they are simple also in terms of how many terms they involve. They just involve the current values of the input and the output and the prior values of the input and the output. So they are rather simple and straightforward.
Yeah. So just getting a sense, you probably said this already, getting a sense of the physical situation. So the capacitor will have a natural frequency and that's given by RC. Like if the charge goes from one side to the other side, like it'll naturally.
I think there you're probably thinking about an LC circuit. So an LC circuit has a characteristic frequency, which is kind of like a pendulum.
Well, yeah, it's like a harmonic oscillator.
So here what has a characteristic time constant is the combination of the resistor and the capacitor. So that has a character, I'll call it a time constant. It sets the scale of charging up or discharging the capacitor. And that is the product of RMC.
So it's like the characteristic time for moving charge from one plate to the other, basically.
Moving one plate, charge from one plate to the other through that resistor.
Through the resistor.
Through the resistor.
And the resistor will.
Yeah. You make the resistor bigger, right? And you're going to move the charge around the circuit more slowly.
Yeah.
And so it's got a longer time constant. And if you make the capacitor bigger, you need to move more charge around. And so it's going to have a bigger time constant. Okay, at this stage, I'm going to go to the code. So here's my code. In my code, this background, before we go into the individual cells, I've got two user-defined functions. One user-defined function is for the low-pass filter that we focused on the details of, and then I've got another one for a high-pass filter. We didn't derive the recursion relation, but I put both filters in my code. Those functions are called with the input signal, meaning they're called with the array of data that represents the input signal, and they return the output signal, the array of data that represents the output. Those functions, as well as being passed the input signal and returning the output signal, they pass two more things that we see are important. The RC time constant and the time interval of sampling, because those two parameters will determine the effect of the filter on the input to determine the output. So I just walk through this code a little bit. I just linger here on the low-pass filter, but there's a high-pass filter here. I'm passing what we were calling X, the input array, and it's going to return Y, the output array. And the code is calculating the output from the input. It needs to know, we wrote our recursion relations down. They involve this quantity that I called alpha, and that quantity alpha had a comparison of these two times, the time interval delta t and the time constant tau. And so both of those are passed. So in the code itself, I just build an array y, initialize an array y of the same shape as the input array. I define my quantity alpha, this comparison of these two different time scales. The first alpha sample is a little bit special. We met this in the leapfrog method, and it's a little bit special here too, because when you've got a recursion relation, your first case or cases is often special because for the third sample, you can't look back at the previous sample. And so you have to make some assumption about the first sample. And there's, probably different assumptions you could make for the first sample. But I'm just taking the first sample as alpha times the input sample. And I'm ignoring any of that feedback. So this is ignoring feedback in the first sample. After I calculated the special case of the first sample, I'm then going to go on and calculate the next sample with this recursion relationship here. And so this one has the input contributing to the output in proportion to the output, and it has the feedback term contributing to the output. So the past output contributing to the current output, also depending on 1 minus alpha. And we said, depending on our values of RC and delta t, we could change alpha from being close to 1 to being close to 0. Those are the extremes. And what you're effectively doing is changing the weighting of the feedback versus the input. And then I just, having calculated the output signal, I just return it here. And the high-pass filter is the same code, except I just changed the recursion relation. The recursion relation is different. The recursion relation for the low-pass filter, what passes through the recursion relation from the low-pass filter is the low pass filter's input. What passes through for the high pass filter is the change in the input. So the difference, really important difference is here, look at this, it's a change in the input value. That's what's entering from the input in the high pass filter. Whereas in the low pass filter, this was just the input value that was entering in the input's contribution to the output. Okay, so let's I don't know what I've done here. And run these. Nothing other than that else in that cell. This cell is where I'm going to explore one of. I've got 3 cells to come, and they explore the step function way of representing or picturing what the filter is doing. The frequency domain is another way, and then finally the impulse way of picturing the performance of the filter. We talked about the step function because I showed you applying steps to the RC circuit. And we talked about the frequency response. We imagined applying sinusoidal frequencies to the circuit. We'll see for the first time the impulse thing. So I'm going to define my RC time constant. Just thinking 1 second. So that's a kind of a reference point for my filter. I'm going to define my sampling rate. So also picking 1 second here. And the number of samples here, 1,000 samples. So we're going to look at it for 1,000 seconds. And then I'm defining my proxy for an independent variable, the time variable. So this is just a time array that runs from 0 to 1,000. I want to define my input, and I'm going to define a step function input. And then we're going to calculate the output and look at the output step function. So I initialize my input array, xi, and then I'm going to set the values of its elements to 1 up until the midpoint of the array. And then the remainder will be the initialized values here. So I'm creating a step that is a whole bunch of zeros and then a transition, which way around it? A whole bunch of 1s and then a transition down to 0. The output of the low pass RC filter, digital filter, which is calculated with this one call to the user-defined function. So I'm passing xi and getting back yi, and I'm passing the parameters dt and rc, and then I just make a plot. So if I run this, so in this case, the magenta is the input. It's a little hard to see the difference. Magenta is the input, and the green is the output. So the magenta is literally the step function that was 1 and then drops to 0. That's the magenta. And then the green is the calculated output with the recursion relation. And the green basically overlays the magenta with the exception that there's a little, it's a little extra time to reach 0. So we apply a step function, and then we see that we don't reach 0. There's a little delay, and that's the time constant. Now that time constant was just 1 second. And so it's a very small time constant here. If I was to go back and let's change this to 10. and rerun. Then we see, well, now we've got an RC circuit that has a 10-second time constant. That's the time scale for responding to the step function. But now there's a tail of about 10 microseconds here. It takes several time constants to reach the full zero voltage here. So we're seeing the time constant. If I was to rerun again with 100, then we're seeing the 100-second time constant. It takes several time constants, so off scale almost, to return to 0 volts.
I was just wondering. Oh yeah. So why did we choose in this case alpha to be where it starts instead of just x0?
Well, that was just a choice.
That's
It's just a choice because I didn't depend on what was before.
Yeah,
the sample. Yeah. So,
yeah. Okay. That makes
so it is like when we had to wait on the string.
Mm-hmm.
We just took a plausible.
It was a plausible first.
Yeah.
Like where we.
Yeah.
Okay.
You see though what the choice was.
Yeah.
I was making here.
Right.
That this is like I had a square wave input and went because I said there was no input on that prior sample. That was basically there was no output on the prior sample. That was my assumption.
Right.
That's tantamount to saying that we started down. We applied the voltage and then we turned off the voltage. So this is the step function approach to looking at the performance of the filter, and the step function approach to looking at the performance of the filter. You basically see directly the time constant, right? We change from 1 second to 10 seconds to 100 seconds. We literally see this then with that time constant. So we're seeing the time constant. It shows you the memory of the filter. So you can think of this RC circuit as having some sort of memory of the past, and the memory is determined by the RC time constant. So if we change it from 1 to 10 to 100 seconds, we see the memory lasting from 1 to 10 to 100 seconds. That's basically what we're seeing. Okay, second cell of calculating. So here I wanted to look at the frequency response of the filter. That's another way of characterizing the filter is by applying a specific sinusoidal signal with a specific frequency and looking at, at most basic level, is that signal pass through the filter? Is it extinguished by the filter? Or is it just attenuated by the filter in some way? What is the gain of that signal? If it passes straight through the filter unordered, then we would say the gain for that frequency is 1. If it was completely extinguished by the filter, we would say the gain at that frequency is 0. And then if it's just somewhat attenuated, then we could describe the attenuation of the signal with that frequency. I've got to make this bigger. This cell is basically a cut and paste of the last cell, except I'm just changing the input and maybe some values. So I'm actually, when I show you, I'm going to keep RC constant at 10 seconds. That was one of the cases we used in the last cell. I'm going to instead try a sinusoidal signal, and I'm going to change its frequency. So this number here corresponds to a frequency of 1 millihertz. And I'm going to increase that 1 millihertz up to 0.1 hertz, so 100 millihertz, to expand that space. Again, I'm defining a proxy for time. Again, I'm initializing an array for my input signal, and then I'm filling the array with the values of the input signal. Now I'm just filling it with a sinusoidal function here, with the frequency that I'm going to adjust. And then I'm just going to calculate the output of the filter, given that input of the filter, and my choices about the RC time constant and the sampling rate, which was one second period. And then I'll make the plots. So the only thing that's different here really is different parameters to show things, but a different signal input. So we'll get a different signal output. Okay, magenta again is the input, green is the output. The frequency here was 1 millihertz, which means it's going to take 1,000 seconds for one complete cycle, which means if I'm plotting 1,000 seconds, I'll see just one complete cycle, which is what I see for magenta. So we see one cycle of a 1 millihertz sinusoidal signal, and then we see the output in green. The output in green almost overlaps the input in magenta with this time constant of 10 seconds. So the frequency of the signal is much lower than the time constant of the low-pass filter. That means that because it's a much lower frequency than this cutoff frequency, that this signal is going to go through the filter. If it's much, much lower than the filter, it's going to be undistorted or unchanged or barely distorted, barely changed. And we see this here. Look, the amplitude of the output is just fractionally lower than the input. The phase of the output is just fractionally delayed. It lags the input. And that tiny change is arising from the feedback that's in a filter. So the input is not exactly, the output is not exactly the input for this frequency. It's close to being the input, but not exactly the input because there's a small feedback. And it's that small feedback that means that the output is not quite in one, and that the phase is slightly delayed, not exactly the same. If we were to increase the frequency, so now if we increase the frequency, I'm going to start walking towards that critical frequency or that time constant. That is this boundary between the world of passing this frequency through the filter or extinguishing this frequency with the filter. So now I've got a frequency that is 10 millihertz. So I'm going to see 10 oscillations in my 1,000-second scale. And so that's what I see in the magenta curve here. As 10 complete oscillations, because each oscillation has a period of 100 seconds because the frequency was 10 millihertz. The green is the output. We see a sinusoidal output now, but now we see that we've walked closer. We walk a lot closer to the time constant of the filter, and now we're seeing that we are attenuating significantly the input when we look at the output, and we're also getting a much more significant phase change, lag of the phase in the output compared to the input. And again, this is all occurring because of that feedback that's in a low-pass filter algorithm that is feeding back some of the previous output into the current input and produces this lag. So we're seeing the lag and the feedback in gain now being, maybe the gain is 80%, 0.8 something, and now the phase change is significant, maybe some 10 degrees or something like that. If I further increase the frequency, so now I'm at a frequency of 100 millihertz, 0.1 hertz. So that's a period of 10 seconds. I'm going to see 100 oscillations on my clock for the input. So the generator is the input. There are a lot of complete oscillations, 100 of them. The green is the output. We see the same frequency for the output, but we see it strongly attenuated as I'm getting close to the RC time constant of the filter. It's strongly attenuated. And well, it's very hard to see on this plot, but there's a big phase difference between the input and the output signal. There's something else that you also see on this plot is that there's this settling time here. And this settling time here has the sort of time constant of the filter. So the filter has a time constant of 10 seconds, and the settling time goes away on the sort of scale of a few of those time constants. And this is the problem that you had mentioned, actually, that we're making an assumption about the prior history of the input when we calculate the output on the first sample. And that assumption actually leaks into the future. You have a memory about that assumption that lasts for several time constants. And so this change here over these first few cycles is this memory of our assumption about the unknown history of the input prior to the first time sample. Okay. The last one I wanted to show you was, and which I didn't discuss in the notes, was the impulse response. And that's this cell here. Impulse just means that you apply to the input of the filter a short, sharp spike, like ideally like a delta function to the input. And then you look at the output response to that filter. And if you apply an impulse, you very directly see the memory of the filter. It will show you a profile of the memory of the filter and how that memory decays away with time. So I'm just going to pick a time constant here. I'm going to change the different values of this. And the rest of the code is basically the same, except that here, my input signal, I'm going to define an impulse. So I initialize an array of zeros, and then for the one sample that's right in the middle of that Tmax sized array, I'm just going to set that one sample to 1. So this is like 500 zeros, a 1, 499 zeros, whatever. So that's what I mean by an impulse. That's my approximation, digital approximation of impulse. We're going to shove that in the filter, and we're going to see what comes out of the filter when you put that spike in the filter. So here's, again, just the call to the low-pass filter function to return the output from that input, and we're going to plot it.
Could be adjusted.
Here it is. So here you can see. And it literally is showing you the memory of that impulse. That it's like an event, How long do I remember it for? Like human.
Right.
So I notice the scale here. The impulse size that I put in was 1. So the magenta input here has gone off scale. And we're just looking at really looking at the green, which is the output here. And we see that that impulse on the input creates a lasting signal on the output, where the amount of time that it lasts for is the time constant, is the memory associated with the RC circuit. So I think I had 20 seconds. And so this is an exponential decay of the memory of that impulse that lasts with a lifetime, 20 seconds. If I was to increase this to 50, then here's the 50-second time constant. Now got a longer memory for a circuit. And if I was to increase it to 100, then we would see a 100-second time constant here. And so these are the 3 ways of characterizing a filter. Just to end up, I just want to show you one other code where I'm just going to show you the plot, basically. So this code here, I implemented my low pass and high pass filters. I just copied those over. And I also made a user function that's going to make a sine wave. What I did in this code here is if you remember the frequency response that we looked at, where we put in the sine wave and we looked at the output sine wave, and when it was low frequencies, we saw it went through the filter, and with high frequencies, it was extinguished by the filter, and when it was somewhere around the time constant of the filter, it was somewhat attenuated. So I added an extra loop to my code for the frequency response in the previous code, which would vary the frequency. So this code here walks through a range of frequencies. And from low frequencies to high frequencies. And when I walk through the high frequencies to low frequencies, I not only calculate the output of the filter based on these different frequency inputs, but this one extra line that I added here calculates the amplitude of the sine wave on the output compared to the amplitude on the input. I put in an amplitude 1 on the input, and then I calculate the amplitude of the output on output. And that is the gain. And I just calculate the amplitude of the output bias and what is the maximum value that I see. So I can interpret that as the gain. And then I make a plot of the gain versus all the different frequencies that I apply to the filter. And this plot is that. So this plot is many calls to low pass filter with a whole range of frequencies, from a very low frequency approaching 10 to the -5 hertz up until a high frequency up here that's getting onto 0.1 hertz, which is, up here is around the scale of the time constant of the filter. So we see at low frequencies, we've got a gain of 1. So the signal just goes straight through. At high frequencies over here, we completely extinguish the signal by some large factor. In between this region here, this is where we're attenuating and lagging this sinusoidal signal. One thing about So low pass, high pass filters are very effective in having a gain of one and smoothly passing the signal, or having a complete extinction of the signal if you have a big, if the signals you want are separated by a lot from the signals that you don't want. So if you have high frequency noise and low frequency signal, or vice versa, then high and low pass filters are great. What they're deficient in, and you see it here, is that transition region from passing the signal to extinguishing the signal, if you want to select signal from noise, is a broad range of frequencies.